Alright, so in this video we'll try to introduce the chain rule, but to do that, let's just see why we did the chain rule in the first place. So suppose we're presented with a function such as this over here, and if we want to differentiate, you can clearly see that we can't just take the derivative of the inside and just square it. Now, if you do that, you may be thinking, oh, wait, hold on a sec, there's a square up here. So can't I just put this 2 to the front and subtract the index, keep what's inside here? Close. You can do that to a certain extent, but there's an extra step after that. So what we can do over here is, you might expect that if we don't know the chain rule yet, you can expand. So first of all, we're going to be rewriting f of x. So let's grab a pen. F of x. Let's rewrite this as the expanded form, 4x squared plus the product of the two, but we're going to multiply it by 2. So 12x is 9. And from here, if you want to differentiate, it's a simple matter of just, well, taking derivative of each component or each term. So when we have f dash, this is going to be 8x, 12x will be just 12, and this 9 over here, well, there's nothing over here, it's a constant. The derivative of a constant is 0, so we're just going to leave it as this one over here. So you can see that there's two-step procedure when we're not using the chain rule, we're just expanding and differentiating term by term. But you can easily see there's a limitation to this. So over here, what if this 2 over here wasn't a 2? What if we're expanding a cubic quartic? Something even larger than that. Now, you can easily see that you're going to run into a lot of problems there. Well, unless you're a super expert at expanding. Now, over here, we're going to introduce the chain rule. So, the chain rule states that if you have the derivative of y with respect to x, you can actually make some substitution of x or some expression, some mini expression inside, such as 2x plus 3 over here, and just replace it with some sort of polynomial u. And if you take the derivative of y with respect to this substituted value u, then it's almost equal to dy dx, but you need to multiply by that substitution with respect to x. So over here, let's just redo this problem up here, but we're going to use the chain rule this time. So just make a barrier here. So remember how over here we said, well, if we have the square, then why can't we just take the derivative of just, let's say, in the form of x squared? But in this case over here, we're going to say that u is going to equal 2x plus 3. Okay, so if this happens, we end up with f of x equal to u squared. So over here, if you have the derivative with respect to u, it's quite simple to do, isn't it? You can easily see that with respect to u, that it's just going to be 2u. But remember that dy dx is going to be the product of this function with respect to u. So let's do this one by one. Now, first of all, let's write down our derivative function. And if we start off with dy du, we know that's 2u. So when we go from u squared, the derivative function will be 2u. So the index goes down, and the index itself is going to be subtracted by 1. So you have an index of 1 over here. When we proceed with the du dx part, so this part over here, we're taking the derivative of u over here with respect to x. So we're going to take the derivative of this expression or this equation that we had at the start. So it's the derivative of 2x plus 3. Well, that's just 2, isn't it? And so over here, we realize that u is actually 2x plus 3. So we're just going to sub all of that back in. So we have 2 times 2x plus 3 multiplied by 2. Just putting that all together will give us 4 times 2x plus 3. And you can easily see that if you expand this expression over here, that these two are actually just interchangeable. There's really no difference between the two, except one is in expanded form and the one on the right is in factorized form. So either way will work. You can probably see in this simple example that expanding and then taking the derivative one term at a time and using the chain rule, in fact the chain rule probably looks a little bit longer in this case, but as the problems get more and more complicated, as these sort of indices become larger and larger, or sometimes you can't even expand it because what if you have a fractional index? Then you can see that the chain rule has got its uses as well. Now, for remembering this rule, you can think of it as a fraction. So if I write down dy dx first, so let's say, sorry, not dy dx, if I write down dy du multiplied by du dx, and if you treat your derivatives here as fractions, what you can actually do is say to yourself, when you multiply two fractions, you can actually cancel out the diagonal terms over here. So du divided by du is really just 1, isn't it? And all you're left with is dy dx, and this is why chain rule will work when you look at the rule as a whole. But otherwise, when you want to find out dy dx, we have to find out what these are one at a time. So first of all, find out what the derivative of y is with respect to u, and then find the derivative of u with respect to x. Okay, so down over here, we're just going to apply this chain rule back into our exponential and strict functions, because we did say before that we can find the derivative using the chain rule. It's just that before we hadn't learnt it just yet, so we just made up an elaborate rule just to compensate for that. So over here, we're going to work at this one, work on the terms one at a time. So we have dy dx equal to, okay, so for the e term over here, the exponential, we're going to say we're going to let u equal to 2x. Okay, we know e to the power of u, oh sorry, dy du. So if we treat all of this as just the little y term for now, we say that dy du, well, e to the power of u is, so the derivative of e to the power of u is actually just e to the power of u. And remember that we need du dx as well, and we're going to multiply this by dy du. So derivative of u with respect to x, we can see that from up here. So if u is the subject here, we want to find the derivative with respect to x. Derivative of 2x is just 2. So you can see over here that your first derivative, this first term, is just 2 multiplied by e to the power of u. But we know this u over here is 2x, just from over here. So we have 2 times e to the power of 2x. Of course, you could have done that from the rule that we learned in exponentials as well, but this is how you would do it using the chain rule. And for the sine term, you can do something very similar. So this time we're going to let u, actually we've already used u, maybe we'll use another letter. It really doesn't matter what letter you use. We'll say let v equal to 5x squared. Now the reason for doing this is because we know the derivative of just sine x, right? So if you had a derivative of just sine v, so let's say this part over here is now a little mini y term, dy dv is the derivative of sine v, and this is equal to cosine v. Okay, and if you want to find dy dx, then we need dv dx as well. So what we're doing here is we're just finding the derivative of this part over here. So the derivative of v with respect to x, while the derivative of 5x squared is 10x. So dy dx for this term is going to be cosine v multiplied by 10x. Or we can say that it is 10x multiplied by cosine of v. We know v is 5x squared, so that's what we're going to write instead. Alright, so for this polynomial over here, you can see that you can expand this and work at it term by term, but if it's to the power of 6, it's quite a big quantity to expand. So what we're going to be doing is we're going to treat this as if it's a single term polynomial to the power of 6. So what we're going to do first is say that this entire chunk inside is going to be u. So let u equal to that chunk inside, which is 4x cubed minus x squared plus 7x. And so if we want to find dy dx, remember that we need the derivative of dy du. Okay, so just note over here to yourself that y is now equal to u to the power of 6, since this entire bracket now is u, and we're going to have it to the power of 6. So dy du is really just going to be 6. So the index of 6 over here multiplied by u to the power of 5. So this index just drops by 1 from an index of 6. Okay, we also need du dx. So we look at the top over here and we think, okay, what's the derivative of u with respect to x? Now work at this one term at a time. So for the first one over here, 4x cubed will turn into 4 multiplied by 3x squared minus x squared. Derivative of that is 2x plus 7, since 7x will just turn to 7. So we get 12x squared minus 2x plus 7. So when you want to combine all of this together, remember that dy dx is equal to the product of dy du multiplied by du dx. So recall that you can remember this rule by thinking to yourself that these two du's can cancel out each other. But what we do know so far is we know what dy du is from up here, and we know what the du dx is from what we just found out here as well. So putting that all together, we're going to say that dy dx is equal to, what do we have up here? We have 6u to the power of 5. So 6u to the power of 5 multiplied by 12x squared minus 2x plus 7. We know u is actually just a placeholder for something. That something is 4x cubed minus x squared plus 7x. So we're going to plug that back in. So we have 6 4x cubed minus x plus 7, sorry, that was x squared plus 7x multiplied by 12. Sorry, it's power 5 here. Remember, it's u to the power 5. And the bracket over here is going to be 12x squared minus 2x plus 7. And that would be your derivative in factorized form. So we could have expanded and derived term by term, but that would have been the derivative in expanded form. And over here, we actually have our derivative fully factorized, and it looks like it's much easier to do it this way rather than expanding as well.